Hello everyone, this is Doug, and in this video we're going to talk about esters. We're going to remind you how to make them, where do we see them in natural products, and do some reactions with them. So first of all, these are a really important functional group in biological molecules. They show up all over the place. There's tons in you. There's tons, I'm sure you've taken medications or pharmaceuticals that have esters in them. They're an important component in smells of things like bananas and all kinds of stuff, pears. I'm going to talk about peaches here in a second. But like if you look at this molecule here, it looks like I've got an ester here, and here, and here, right? This has 3 esters, and this molecule, if you're not familiar with it, this is a triglyceride. Right? A triglyceride, which is also known as an oil or a fat molecule, right? So like fats like butters or on your stomach, and oils like olive oil or coconut oil or something like that, right? The triglycerides. But you notice that it's connected. What you do is you took glycerol and you connected it to 3 fatty acids through esters. It's really important. Similarly, if you take a look at the molecule just to the right of it looks like I have 2 more esters. Right, I've got these 2 esters right here. This would be a phospholipid. This is a phospholipid, hence because of the phosphate. But this is a phospholipid. And if you've taken any biology at all whatsoever, you know that phospholipids, right, make up the cell membrane. It's called the phospholipid bilayer, right? Super important. Again, it has esters. Down here, this is a molecule. Again, here's an ester, but this is a pharmaceutical, right? This is a drug that some folks have made. It's got an ester in it, so we want to know how to make those. They show up. You may already recognize this, right? Here's an ester in this thing. This is aspirin. Good old acetyl salicylate. So we've got aspirin here. And then I put this one down here. I mentioned smells. Here's another ester. This is a component. There's many components, but this is a component in fruits like peaches and nectarines and stuff like this. I love the smell of peaches, so I figured I'd put this one. Where here we have a cyclic ester, also known as a lactone. I should write that down. If you ever hear the term lactone, that's just a cyclic ester, right? So that the ester is part of a ring. None of these other ones are lactones. But the point is that you see esters everywhere. They're all over the place. Now, where do they fit into our scheme, right? Esters are down here. So they're not the most reactive of our carboxylic acid derivatives, right? Here's kind of the line that I separated before. The top ones were really reactive to water, right? So these readily react with water. Whereas esters do not. They do not react with water. Which makes sense, again, right? Because, again, we have lots of phospholipids in us. We have lots of triglycerides in us. We have lots of water in us. We have, peaches have water in them. That molecule, that lactone, doesn't just fall apart because there's water around. So what we have to do is we do have to use either this acid catalyzed or base-mediated hydrolysis in order to turn our esters back into carboxylic acids. And so really, you can turn esters into amides directly, and that's kind of about it. And even that's kind of hard, and I'll talk about that in a little bit. But if you want to turn esters into some other carboxylic acid derivative, you're going to go through the carboxylic acid itself, and then go to the acyl halide, etc. So how do we make them? Just a reminder from carboxylic acids, if I had a carboxylic acid that looks like this, and I wanted to make an ester, I can add kind of really whatever alcohol I want. And the idea is that I need acid catalyst. I need to heat it up like crazy and drive off. So 1, 2, 3 carbons, 1, 2, 3 carbons plus water. I need to drive off that water in what we called, right, the Fischer esterification. All right, remember this is called the Fischer esterification. It works. It is historical, but it's time consuming. It wastes a lot of energy, and your yields are not always great. Much more efficient and faster to use acyl halides. Acyl halides have the disadvantage of that you have to make them, and you have to be very, very careful of any water that's around. But you can just kind of take whatever alcohol you want, take whatever acyl halide you want, let them just look at each other, and it's done. Right, and it just finishes. Usually there's some kind of base here like triethylamine or pyridine, but very, very quick, very easy way to make whatever desired ester you want. Super fast. In a similar vein, if you use an anhydride, let's use a ethanoyl anhydride, so I'll use, or actually propanoyl, and you add whatever alcohol you want. I'll use phenol in this case. Again, there'll be some sort of base to pick up the hydrogens that are produced, but it's the same sort of thing, right? So remember that with the anhydrides, whatever this group is, that's the group that's going to end up on your alcohol. So I had a 3-carbon piece, so I'll draw a 3-carbon piece, right? And then the side products would be the acid. So we know ways to make esters, right? We have at least these 3 ways to make esters right now. Actually, there's a 4th. I didn't even think about it. But also, just as a side note here, don't forget about the Baeyer vinegar. Don't forget about that Baeyer vinegar oxidation where you take a proxy acid and a ketone or aldehyde. I guess it'd have to be a ketone to make an ester, but you take a ketone, add a proxy acid, and it does that migratory insertion sort of thing where the R group transfers into O to make an ester. So you also have the Baeyer vinegar. Now the reactivity, it is just kind of that general addition elimination reaction, right? All of these carboxylic acid derivatives behave really similarly. So you definitely have your hydrolysis reactions, right? I know I can go back to make the carboxylic acids. What you also can do is if you heat up an ester in the presence of a different alcohol, right? So notice that I put R prime before there's an R single prime here, and then here's an R double prime. If you heat this up, you can actually change the ester so that you end up freeing that original alcohol that was on there, and you make a new ester. This is sometimes called a transesterification. And again, you just heat them up like crazy. An example of that would be something like this. Maybe you had a methyl ester and you decided that for whatever reason you really needed it to be a butyl ester. You could just heat them up like crazy and they will switch out. Usually this is driven by the fact that the alcohol that's being switched out is smaller and therefore it can be boiled away so that you drive it forward using Le Chatelier's principle. But it's a way to change one ester type into another ester type, transesterification. And then lastly here, we have making an amide, where if you take an ester, you add lots of an amine, high temperatures, you can just do a basic addition elimination with that amine, kind of like you would with any other one. Again, esters are not that reactive, so you really have to kind of grind on them and really add a lot of energy in order to get that substitution to take place, that addition elimination. So those are kind of your basic reactions. What I will talk about in a different video is the Claisen condensation. And that's a way to take 2 esters and make them condense. You make a water molecule. It's kind of like the aldol condensation, but a little bit more straightforward. And I'll talk about that again in a different video. But it's a very, very common reaction of esters that you should know. Now, mechanism here, right? So I'm going to just show you a couple of mechanisms for esters so you just get a good feel for them. Here I have the base-mediated hydrolysis. Base-mediated hydrolysis conditions. So I'm going to go ahead and take a look at my reagents, right? My reactants. I've got a partial negative, partial positive. Looks like I've got an Na plus and an OH minus. Now this is going to behave like most all of your carboxylic acid derivatives. The OH is going to be attracted to that partially positive carbon in the carbonyl. Those electrons kick up from the pi bond because they're the weakest. If I take a look at this, I've got this step here where I have my negative O now. I have an OH, and now I have my O ethyl. And like I was saying before, right, always you ask yourself, well, when these electrons from this oxygen drop down, is there something that's a good leaving group that can leave? Is it going to be the phenyl group that leaves? No, because that would be a negative carbon on an aromatic ring, which is doubly bad. Could it be the OH that leaves? Yes, it could. That's why this step is reversible. That'd just be going back to where you started. Totally true. Or could the O-ethyl group leave, right? The ethoxy group, this alkoxide group. And so let's take a look at what happens if that leaves. Now, it's not the greatest leaving group in the world, right? It's going to be an O-. But what's amazing about this, you'll notice that I didn't draw a reversible arrow for this step, because you will not see your ethoxy add back in to the carbonyl like this. It's not going to happen. Might be asking, well, why not? And that's because remember that this is a carboxylic acid that you've just made. A carboxylic acid, right? This hydrogen is acidic. And if you're paying attention, right, you'll notice that here you made ethoxide. You have a localized negative on an oxygen, which is a strong base. And so all that's going to happen here, I'm going to go ahead and erase the red arrows so that I don't confuse us, but the red arrows are for no. We are not going to go backwards, right? So there is no back reaction here. This is not reversible. So I'm going to erase all this red. What happens instead is that you just do an acid-base reaction. Because remember, acid-base reactions are super fast. They're really, 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 really quick. And so you just do, you can't add back in, and then you have this irreversible acid-base reaction because they have such different stabilities. And then HO, and you've made ethanol. And now you haven't made your carboxylic acid quite yet. You have the carboxylate here, right? This is just a carboxylate. And that's why we then bring in step 2 here, which is your acid workup. So now you just add some H+ so that you can reprotonate your carboxylic acid to give you your product. And that's how you hydrolyze an ester back to the carboxylic acid, right? The base-mediated hydrolysis. And again, I was saying, I don't know if you remember back in that previous video, the base-mediated hydrolysis is awesome. And the reason it's awesome is because it's irreversible. Right? Because of these steps right here, we said that this was a one-way step and this is a one-way step. The acid-base one actually might have a little bit of reversibility to it, but this step right here is the key part. And if you remember, I think I did an acid-catalyzed hydrolysis of an ester in a previous video, or maybe I did the esterification. But either way, if you go back and look at that mechanism, every single step is reversible. The yields kind of suck. The starting stuff is about as stable as the ending stuff. And so you don't get great yields unless you really are smart and careful about the reagents that you choose and pulling out product as you go. Here, the base it adds in. It's a one-way reaction, and you tend to get good yields. So I want to show you this mechanism. Base-mediated hydrolysis is awesome. If you do the base-mediated hydrolysis on an ester, sometimes that's called saponification, and I'll just write that down here. If you hear the term saponification, they're talking about the base-mediated hydrolysis of an ester. Base-mediated hydrolysis of an ester. So if anyone's ever made soap before, which a lot of our students have, right? If you've made soap before, you've done a saponification. And that's because you took an ester, which was a triglyceride from that first slide, add a bunch of hydroxide. It does a hydrolysis. It frees everything and makes little soap molecules. One thing we haven't shown yet that is interesting is, well, what if I have one of these carboxylic acid derivatives and I use a Grignard reagent on it, some organomagnesium or even organolithium compound? Like what will happen? What will that look like? So let's take a look at that mechanism. So step 1, I'm adding the CH3 MgCl. Remember, that could be MgCl, Br, I. The halogen's not that important. And again, I have my partial negatives here, partial positive there. So same first step, right? I'm trying to impress upon you that the reactivity of these carboxylic acid derivatives are all very, very similar. So I'm not going to show you every possible combination, but you should be able to figure the mechanism out just because it's so redundant. So I've got my Grignard reagent, right? And I guess I should put partial charges on that. Magnesium's got a big old partial positive, and this carbon's got a big old partial negative. And so what we see is that my negative carbon, that nucleophile, is going to attack the carbonyl. Again, those electrons kick up. I'm going to take a look at my intermediate, that tetrahedral intermediate. So now I've added a CH3 and I have an O ethyl. Same question, if these electrons drop down, what can they kick out? Am I going to kick out a phenyl minus? No. CH3 minus? No, but right, because those are both so unstable. Or an O minus, that's the most likely thing, right? The O minus, because that'll be the most stable thing. And you're replacing a negative O with a negative O, so that's kind of a wash. And also it's favored entropically because you go from 1 molecule to 2 molecules. So I have my double bond back, and now I have a methyl and my ethoxide. And that's all fine and good, but the problem here is that you just made a ketone. And you started with an ester. And if you go back and you remember the relative reactivity of carbonyls, specifically ketones versus esters, ketones are very reactive. Right? Remember, aldehydes were the most reactive and ketones are right behind it, whereas esters are not very reactive. They're not very electrophilic. And so what's going to happen is your Grignard reagent, yeah, you're going to reduce a couple of these esters, but then they're going to form ketones, and ketones are more reactive than the esters are. So as soon as you get ketone, your Grignard, your Grignard reagent is going to go and attack that ketone because it's more reactive. It's going to be a faster reaction. And so what happens is that your reagent is then going to attack the carbonyl. Same thing, I get a tetrahedral intermediate, O minus, a CH3, and a second CH3 now. I've just added a second CH3. And I ask myself the same question, can I take some of these electrons and drop anything down? But in this case, the answer is no. I can't take those electrons drop down because I can't kick out a phenyl minus, a methyl minus, or a methyl minus. So that means that the O just stays negative like that. And then you just chill out, right? That's just going to stay there until you add the step 2 stuff, which is your acid workup, just to protonate stuff. And then you'll get your product. So you'll have the phenyl group, an alcohol, and 2 methyls. And that's going to happen with your Grignard reagent and any really of those carboxylic acid derivatives. You're going to end up adding 2 of them. The only exception's going to be the nitriles, but let's not worry about that. But you're going to end up adding 2 of them, right? So the idea here was that you had a CH3 group. Notice that there is excess, and so you end up with 1, 2 of those groups on there. It would be the same thing if you had an ethyl Grignard or a vinyl Grignard or an allyl Grignard or a phenyl Grignard. Whatever the Grignard reagent is, and if you react it with something like an acyl halide, an anhydride, an ester, an amide, it's going to add twice. It's a lot like what I was talking about in the LAH versus diabol video, where you're going to add twice. You're going to reduce it twice is the idea. So keep that in mind. Grignard reagents will add twice for esters. Now let's look at some examples. I try to make these fairly redundant. I have the same starting material here for all of these just to kind of emphasize for you some of these reactivities here. If I look at the first one, I got esters for all of these, so let's get that out of the way. Actually, I'm going to go ahead and ask you to pause. Go ahead and pause, see what you can do for these 5 reactions. This last one is a bit of a synthesis, right? So how am I going to make that thing? So why don't you pause, take a minute, and we'll come back and go through this together in just a sec. So if I take a look at this, right, first one, this just looks like acid catalyzed hydrolysis. So I've got acid, I've got water, I've got heat. Sounds great. So I'm just going to hydrolyze that carboxylic acid. So that means I should just end up with my carboxylic acid and then my alcohol that I removed. In the second one, I have just water, which is not good enough to do anything, right? Esters are resilient to water. They're not going to react with water. Water is not a strong enough nucleophile. There's no acid to protonate your carbonyl in your ester to make it more electrophilic. There's no strong base to go and attack it. There's nothing going on there, right? Water is not going to do anything to an ester. So you don't have to worry about if water's around when you're dealing with an ester. In the third one here, I have LAH, right? That's my lithium aluminum tetrahydride. That's the sucker that can fully reduce, right? It's going to add multiple hydrides to my ester, so it's going to take it all the way down to an alcohol. And if that doesn't sound familiar, then definitely go and watch that video that I posted. So you'd end up with 2 alcohols here because these 2 hydrides end up here and here. Right? So I ended up adding that hydride and adding that hydride. Versus diol, we said just added 1 hydride, right? So I had 1 hydride. We said LAH was more like 3, a little over 3 hydrides. And so LAH is going to give me the aldehyde. And then you'd get the corresponding alcohol. And then so what's going on with this one? I want to turn an ester into an amide. You have 2 routes. The one route is just really direct, which is just to add this amine. So 1, 2, and just heat the crud out of this. Add tons and tons of this amine and just heat it like crazy. Now that might be fine. That might be fine. This amine, though, might be kind of a problem because it's just ethylamine, which is pretty small, and so it has a really low boiling point. So keeping it mixed with your reagents while you're heating it is going to be annoying. You're probably going to have to seal it, make a bomb, which has its own issues, use a blast shield, all that kind of stuff in case it pops on you. So that while that works on paper, probably not so much in reality. What might be easier to do, but a lot more steps, is to take this, go ahead and hydrolyze it with, let's do my favorite one. Let's do the base-mediated. So step 1, add hydroxide. Step 2, add acid. So that I turn this into the carboxylic acid. Then I would just isolate that, sprinkle in a little SOCl2 and maybe some triethylamine or something to turn it into that nice, super reactive acyl chloride. Again, from here on out, all these reactions are done at room temperature. And then I can just add my amine that I wanted. Again, excess, I need at least 2 equivalents of this. And I get my amide. And it would be really high yield, very straightforward, no bombs, don't have to like boil anything to death. So that'd be another way to do it, where I go to the carboxylic acids, get a really nice reactive acyl halide, and then just throw in the amine that I want. So anyways, I hope those examples help you out with some of the reactions of esters. I will do a video on the Claisen condensation to kind of help you out with that. Happy studying. Good luck.